So very good morning to all of you present over here. Today we are going to do Valence Bond Theory, which was in the further continuation with the VSEPR theory, which is electron pair repulsion theory. Okay. Okay. So today we will do VBT, Valence Bond Theory. What is Valence Bond Theory? It was based on the quantum mechanics. Okay. So this theory primarily focuses on the formation of individual bonds from atomic orbitals. Okay, so the overlapping of atomic orbitals can form individual bonds. Individual bond from the atomic orbitals of the participating atom during the formation of a molecule. Okay. Okay. So now comes to the valence bond theory, which is formed by the quantum mechanism, and it is formed by the formation of individual bond from the atomic orbital of the participating atom during the formation of a molecule. So according to VBT, electrons in a molecule occupy atomic orbitals rather than molecular orbitals. Okay, wait for a second. Okay. So electron in a molecule occupy atomic orbitals rather than molecular orbitals. Okay. So this is what the basic principle for valence bond theory is. The atomic orbital overlap on the bond formation, and larger the overlap, stronger is the bond. Okay, this overlapping is there of the bonding orbitals. Like if I'm taking two p orbitals, then this gives me pxy, pyz, pxz. Okay, like this. Overlap of the bond formation, and larger the overlap, the more stronger the bond is. Okay. The metal bonding is essentially covalent in origin, and metallic structure involves resonance. Okay. Metallic bonding is covalent in origin. Okay. And metallic structure involves resonance of electron pair bonds between each atom and its neighbors. Okay. So in this pair, the electron pair bonds between each atom and its neighbors is there. The metal bonding is essentially covalent in origin. Covalent bond is formed by the sharing of electrons, and metallic structure involve resonance. And resonance, as we know, that there should be a doubly bonded system in which the electron pair bonds shift towards each other so as to perform a resonating structure. So the Lewis approach of chemical bonding failed to shed light on the formation of chemical bonds. Okay. Lewis approach does not tell us that how the chemical bonds are formed. Okay. Also, VSEPR valential electron pair repulsion theory had limited application and also failed in predicting the geometry corresponding to complex molecules. Now, in order to address these issues, the valence bond theory was put forth by the German physicist Walter Heinrich Hitler and Fritz Wolfgang London. So the Schrödinger wave equation was also used to explain the formation of a covalent bond.
Okay, so the Lewis approach of chemical bonding failed to shed light. Okay, we know that. It does not tell about how chemical bonds are formed. Also, valential electron repulsion theory, valential electron pair repulsion theory, had limited application and also failed in predicting the geometry corresponding to complex molecules. Okay, so in order to address these issues, these two scientists gave the Schrödinger wave equation was used to explain the formation of a covalent bond between two hydrogen atoms. Okay, the chemical bonding of two hydrogen atoms is illustrated below. So the VBT theory, okay, the valence bond theory is focusing on the concept of electronic configuration of atomic orbitals and their overlap and the hybridization of these atomic orbitals. Okay. So chemical bonds are formed from the overlapping of atomic orbitals wherein the electrons are localized in the corresponding bond region. Okay. So how the covalent bonds are formed? There should be the localization of the electron. This electron, if it is going from here, then it will come over here also on both these carbon centers. Okay. So this electron is sharing to this also, and it belongs to this carbon. And similar way, this carbon is of this carbon, and it is sharing itself to the another carbon, like this. So localization in the corresponding bond region. Okay. So The valence bond theory also goes on to explain the electronic structure of the molecule formed by this overlapping of atomic orbitals. Okay, how the structure has been formed by the overlapping of these atomic orbitals. Okay, it also emphasizes that the nucleus of one atom in a molecule is attracted to the electrons of other atom. Okay, what it emphasizes on, focuses on, that the nucleus of one atom in a molecule is attracted to the electrons of the other atoms. Postulates of valence bond theory. The important postulates of valence bond theory are: covalent bonds are formed when two valence orbitals half-filled belonging to two different atoms overlap each other. Okay, so when I am having two orbitals, half-filled orbital, if I take off P, this is half-filled orbital, belonging to different groups atom overlap to each other. The electron density in the area between the two bonding atoms increases as a result of this overlapping, thereby increasing the stability of the resulting molecule. Okay, so electron density increases in the area between the overlapping bonding atoms, and as a result of this overlapping, increasing the stability of the resulting molecule. The presence of many unpaired electrons in the valence shell of an atom enables it to form multiple bonds with the other atoms. Okay, so these unpaired electrons, like it is having the p in the p orbital, 6 electrons can be filled. It is just having 3 electrons, so 3 more electrons can be filled over here. So it is half filled. Okay, so the presence of many unpaired electrons in the valence shell of an atom enables it to form multiple bonds with other atoms. The paired electrons present in the valence shell do not take part in the formation of chemical bonds. Okay, paired electrons are stabilized by themselves, so they will not take part in the chemical bond formation, as per the valence bond theory. So covalent chemical bonds are directional and are also parallel to the region corresponding to the atomic orbitals, okay, that are overlapping. So covalent bonds have a direction and are also parallel to the region corresponding to atomic orbital region. Like this is what the parallel overlapping is. The sidewise overlapping is like this. So, okay, so this is parallel overlapping, this is sidewise overlapping, you will see. So sigma bonds and pi bonds differ in the pattern that the atomic orbitals overlap. Pi bonds are formed from sidewise overlapping, whereas overlapping along the axis containing the nucleus of the two atoms leads to the formation of sigma bond. Okay, so here this is our sidewise overlapping, this is parallel overlapping. So the pi bonds will be always formed by the sidewise overlapping, whereas overlapping along the axis containing the nucleus of the two atoms leads to the formation of sigma bond. Here sigma bond will be formed, and here pi bond will be formed. Okay, this is your sigma bond, and this is your pi bond. So here we get the pi bond and sigma bond. Like if I will talk about the sigma bond, it is formed at the axis, around the axis of the nucleus of the two atoms. Okay, so sigma bond is formed by the, and how pi bond is formed? Pi bond is formed by the, like if Py, Px and Pz and Py, these are the axes of the various p orbitals. This is what the sp orbital, this was my s orbital, and this is the p orbital overlapping. So sigma bond is formed. Here also sigma bond is formed. But p orbitals, pi bond, how it is forming? At the sidewise overlapping of Py, Py and Pz orbitals. Okay, Py, Py and Pz orbitals are forming the, so from sidewise overlapping, whereas the overlapping along the axis containing the nuclei of the two atoms lead to the formation of sigma bond. So sigma bonds and pi bond differ in the pattern. Okay, and we have seen that pi bonds are formed from sidewise overlapping. Now number of orbitals and the types of hybridization. According to valence bond theory, the metal atom or ion under the influence of ligand can be used as if N-1d, NS, NP, or NS or NP or ND in the valence shells. These are the various orbitals, sp, d, and f orbitals, for hybridization to yield a set of equivalent orbitals of definite geometry. Okay, so if I'm having the definite geometry is there for the particular hybridization. Okay, So what can be the like equivalent orbitals are there such as octahedral, tetrahedral, square planar, and so on. These hybrid orbitals are allowed to overlap with ligand orbitals that can donate the electron pair for bonding. Okay. Now, these are the various orbitals and the type of hybridization which is seen. Like if we see the coordination number of 4, then the sp3 hybridization will be there with the tetrahedral shape or the geometry. The sp2 orbital can be seen with the coordination number of 4, having the square planar shape. With 5 as a coordination number, sp3d orbitals can be seen, trigonal bipyramidal shape is there. With 6, sp3d2 or d2sp3 with the shape of octahedral. Okay. In case of 4, there are two shapes, tetrahedral and trigonal planar can be tetrahedral and square planar can be seen. In case of 5, it is trigonal bipyramidal. In case of 6, it is octahedral and dsp2 or d2sp3. sp3d2 or d2sp3. Applications of VBT. The maximum overlap condition, which is described by the Valence Bond theory, can explain the formation of covalent bond. Maximum overlapping gives the maximum stability, and thus the formation of covalent bond is favorable. So this is one of the most important applications. Like if we see the difference in the length and strength of chemical bonds in hydrogen and fluorine molecules, it can be explained by the difference in overlapping orbitals. Okay, covalent bond in HF molecules form the overlapping of 1s orbital of hydrogen and 2p orbitals belonging to the fluorine atom. Okay. More electronegativity is also there in case of fluorine as compared to hydrogen. That is why also, and 1s and 2p are more favorably overlapping is very much, difference is very less, overlapping is more, therefore it is more stable, tend to be more stable, F2 as compared to H2. Then limitations of VBT. The shortcoming of valence bond theory include failure to explain the tetravalency exhibited by carbon. It was not able to explain that why carbon shows the tetravalent character. Okay, either it can lose or gain, but how it is forming the covalent bond by the sharing of electrons with the other so as to satisfy its valency. The theory assumes that electrons are localized in specific areas, but electrons are delocalized. Okay, they are continuously showing resonance. Okay, so it does not give a quantitative interpretation of the thermodynamics or kinetic stability of coordination compound. Okay, it does not give the quantitative interpretation. Quantitative interpretation is like how much quantity is there or the whether the reaction of thermodynamics. Now, if thermodynamics or kinetic stability is we see, thermodynamics is whether the reaction will proceed, the formation of reactant will be there. Okay, formation of product will be there from the reactant. How much more we have to take so as to form the product, or kinetic stability of the coordination compounds. Kinetic stability over here are the stabilities, like if we know kinetic energy and potential energies are there. So how much stable my molecule is. No distinction between weak and strong ligands. Okay. There is no distinction that how much weak or strong ligand is their coordination compound has been formed in the ligand case or not. Okay, like that. No explanation for the color exhibited by the coordination compound. Like different colors are exhibited by the different coordination compounds. Okay. So the valence bond theory fails to explain the tetravalency and provide insight, also fail to provide insight into the energy of the electrons. This theory also assumes that electrons are localized in certain areas. Okay, so overlapping of orbitals. Positive overlap and negative overlap. So positive overlap is between the px-px or pz-pz orbitals. So positive charge overlap each other in negative or overlap, positive overlaps with the negative overlap. Okay. So next comes the impositive overlap, the sp overlap, and if it is the sp hybrid orbital, positive charge of the s orbital and negative of the no lobe, like lobes are there, different lobes are there. These are the lobes. This is the positive lobe and negative lobe. So if the positive lobe is overlapping with the positive lobe of the pp orbital, sp orbital, PP overlap, this is sidewise overlapping, this is parallel overlapping. Okay, this is PY overlapping, this is PXS overlapping along the Z-axis. So here we are taking internuclear axis as Z-axis. Z-axis is the internuclear axis. So this was for the negative overlap. Negative overlap with the positive orbital lobe will overlap with the negative lobe. Okay. Here in PX orbital, the positive lobe was overlapping with the negative lobe and vice versa. In the PY orbital, negative lobe was overlapping with the positive lobe and positive lobe was overlapping with the negative lobe. In the zero overlap, what is happening? The negative and the positive overlap are just here in the positive overlap, they are overlapping with the positive lobe of the s orbital, but here there is no overlapping. Okay, so positive, negative, and zero overlap of s and p orbitals. Okay, so this was negative overlap, where the zero overlap is where there is no overlap between the orbitals. Okay, like this. So the atom combine by colliding with each other. But what does this mean at atomic level or atomic level? Okay. So the valence bond theory failed to explain the tetravalency of carbon and also fails to explain the insights into the energy corresponding to the electrons. Okay. So these were the positive, negative, and zero overlapping between the different s and p, 3p orbitals of px, py, and pz. The atom combines by colliding with each other, but what does this mean on atomic level? This situation refers to the process in which the two atoms come so close to each other that they penetrate each other's orbital and form a new hybridized orbital, where the bonding pair of electrons reside. Okay, so what they are telling here is that atom combines by colliding with each other. But what does this mean at atomic level? Atom combines by colliding with each other to form a molecule, but at the atomic level, how do they overlap? So this situation refers to the process in which the two atoms come so close to each other that they penetrate each other's orbital and form a new hybridized orbital. Okay, this hybridized orbital when the bonding pair of electrons reside. This hybridized orbital has low energy than the atomic orbital and hence are stable, and it is in the minimum energy state. This partial penetration of the orbital is known as orbital overlap. Okay. So the extent of overlap depends on the two participating atoms, their size, and the valence electrons. Okay. So how much they are overlapping? It depends on their size and the valence electrons. In general, the greater the overlap, the stronger is the bond formed between two atoms. Thus, according to the orbital overlap concept, atoms combine by overlapping their orbital and thus forming a low energy state. Okay, they want to attain a stable state configuration, where their valence electrons with opposite spin pair up to form a covalent bond. The importance of orbital overlap was emphasized by Linus Pauling while explaining the molecular bond angles observed through experimentation and is the basis for concept of orbital hybridization. Okay. Now, directional properties of bonds. The molecular bond angles were explained through the directional properties of the bond, and the molecule of hydrogen is formed by the overlap of 1s orbital on head-to-head collision. Okay, like this hydrogen. Okay, so 1s orbital is there for the hydrogen. Overlapping of atomic orbitals. When two atoms comes in contact with each other to form a bond, their overlapping can be positive, negative, or zero depending upon the phase. Okay, so positive overlapping of atomic orbitals. When the phase of two interacting orbitals is same, then the overlap is positive, and in this case, the bond is formed. Okay, so the phase of two interacting orbitals, positive or negative, comes from the sign of the orbital wave function and is not related to the charge in any sense. Okay, it just comes from the wave function. As we have seen that the Schrodinger wave function was there. So negative overlapping of atomic orbitals. When the phases of two interacting atomic orbitals is opposite, then the overlap is negative, and in the case the bond is not formed. Okay. Then zero overlapping of atomic orbitals. When the px and py orbitals don't overlap, this is called as zero overlapping. Then sigma and pi bond formation. There can be a head-to-head overlapping. Here we can say there can be a head-to-head or coaxial overlapping. There can be a head-to-head coaxial overlap, and head-to-head coaxial overlap of forming a sigma bond. Here sigma bond is forming, here sigma bond is forming, and here sigma bond is forming. So 4 ways to form a sigma bond. Sigma bonds and pi bonds are types of covalent bonds that differ in the overlapping of atomic orbitals. Okay. So covalent bonds are formed by the overlapping of atomic orbitals. Sigma bonds are a result of head-to-head overlapping of the atomic orbitals, whereas pi bonds are the lateral or sidewise overlapping of two atomic orbitals. Okay. So like this head-to-head overlapping of hydrogen bond can be formed from the coaxial axis at the third position. We see this can be hydrogen. Example of hydrogen. Then various bond parameters such as bond length, bond angle, and bond enthalpy depend on the way the overlapping of atomic orbitals takes place. Okay. So this overlapping occurs in the two major ways, giving rise to the primary two types of bonds, sigma and pi bonds. Okay. So sigma bond. The sigma bond is a single bond. Okay, it is a covalent bond formed by the head-on positive same phase overlap of atomic orbitals. Head-to-head overlapping is there in the sigma bond. Okay. Along the internuclear axis. Sigma bonds are the strongest covalent bond owing to the direct overlapping of the participating orbitals. The electrons participating in a sigma bond are commonly referred to as sigma electrons. Okay. Those electrons which are participating in the formation of the sigma bond, they are referred to as sigma electrons. Generally, all sigma bonds are single bonds are sigma bonds. They can be formed via the following combination. Okay, SS overlapping can be there. Okay. So one s orbital from each participating atom. Undergoes head-on overlapping along the internuclear axis. An s orbital must be half-filled before it overlaps with another. It has to be half-filled. Okay, otherwise how it will be able to pick up the electrons? The overlapping of two s orbitals resulting in a sigma bond is illustrated above. This type of overlap occurs in hydrogen molecule where each hydrogen atom has half-filled s orbital. Okay, so if we talk about the like s orbital, 1s. So half-filled orbital. Here 1s is having half-filled orbital. So what they will do, 1s is fully completed like this. Okay. So this is the overlapping of 1s and 1s orbitals. sp overlapping. Here one half-filled s orbital overlaps with one half-filled p orbital along the internuclear axis. Okay. One half-filled s orbital is there and one half-filled p orbital is there. So overlapping is there in the s orbital and p orbitals are 3. So one half-filled p orbital is there. So this is due to the overlapping of sp orbitals. Okay. Along the internuclear axis forming a covalent bond. This condition is illustrated below. This type of overlapping can be observed in ammonia, NH3 molecule. Okay. Featuring 3 sigma bonds. These are the 3 sigma bonds formed by the overlap of 2px, 2py, and 2pz orbitals belonging to the nitrogen atom, and 1s orbital of the 3 hydrogen atoms. Okay. So here, what the orbitals are. These are the p orbitals and s orbital fusion of the hydrogen. These are the s orbitals and these are the px, py, and pz respectively. Okay. Now pp overlapping. In this condition, one half-filled p orbital from each participating atom undergoes head-on overlapping along the internuclear axis. Okay. Head-on overlapping is there in the pp overlapping where the pi bond formation takes place. Okay. Sidewise overlapping, we can say. And here in the sigma bond, we know that it is always the overlapping of the head-to-head overlapping. Okay. Here head-to-head overlapping is there and here sidewise overlapping is there in the pi bonding formation. Okay, so a Cl2 molecule always have a pp overlapping. So because chlorine is having a double bond system, 7 are there. How this is pp overlapping is there? Sidewise overlapping, if I will assume then like this sidewise overlapping of the 3pz orbital of 2 chlorine atom. It is important to note that head-to-head overlapping of 2p orbitals gives a sigma bond, whereas the lateral overlap of these orbitals lead to the pi bond. Okay, if the head-to-head overlapping is there, like over here, head-to-head overlapping, this is sigma bond. But if there is lateral overlapping is there, then they will give the formation of pi bonds. Okay, so here the half-filled p orbitals each participating, and there is head-to-head overlapping. So there will be a sigma bond, chlorine, chlorine. Single bond will be there. Then comes pi bond. Pi bond is formed by the lateral or the sidewise overlapping of the 2p orbitals along the direction of the perpendicular axis to the internuclear axis. During the formation of pi bond, the axes of the atomic orbitals are parallel to each other, whereas the overlapping is perpendicular to the internuclear axis. Okay, so these both are parallel to each other, but here the overlapping is perpendicular to the internuclear axis. Like if I will make this as an internuclear axis, so this overlapping is parallel to this internuclear axis. Okay. So whereas the overlapping is perpendicular to the internuclear axis, this type of covalent bond is illustrated below. Pi bonds are generally weaker than sigma bonds owing to the significantly lower degree of overlapping. Okay, pi bonds are less stable and they are weaker because there is very less overlapping. Okay, head-to-head overlapping is very much stronger as compared to the sidewise overlapping or the lateral overlapping, which has been seen in the pi bond, where they are parallel to the bonds overlapped bond which has been formed are parallel to the internuclear axis. Generally, double bonds consist of one sigma bond and one pi bond, whereas a triple bond consists of two pi bonds. So if I talk about a double bond and a triple bond. So it is having one sigma and one pi bond. It is having 2 pi and one sigma bond. How this is 2 pi? This is 1 pi and this is 1 pi. Okay. This is 1 pi and this is 1 pi. So these are 2 pi and 1 sigma. Okay. So double bond consists of one sigma and one pi bond, whereas a triple bond consists of a 2 pi bonds and a 1 sigma. It is important to note that a combination of sigma and a pi bond. Okay, so it is important to note that a combination of sigma and pi bond is always stronger than a single sigma bond. Okay, so triple bond is very much stronger than a single sigma. So double bond and triple bond combination, when there is a sigma and pi bond combination is there, then they are quite much stronger. So SS orbital overlapping, then PP overlap can be there. This is what our like S head-to-head overlapping. Here also head-to-head overlapping is there of both the S and P orbitals. Okay. The difference between sigma and pi bonds. Sigma bond are single bonds. These are overlapping due to pure orbitals, can be due to pure or hybrid orbitals. The overlapping orbitals must be unhybridized. Okay, they should not have any hybridization. Unhybridized, we can say that like if my orbitals PP orbitals, there should not be any further prior overlapping. Okay, there should not be any hybridization. So these bonds are strong and have high bond energies. Okay, these are very strong. These are relatively weak. Pi bond comes in double bond and triple bonded system and can exist independently, must exist along with a sigma bond because it is having one sigma bond. It is also having one sigma bond. Two pi bonds are there, one pi bond is there. Has an impact on the shape of the molecule, has no role in determining the shape of the molecule, means it does not have any hybridization. The orbitals overlapping of the orbitals must be unhybridized in case of pi bond system. Okay, so this was for today. Hope you understood the VBT theory. Okay, and the hybridization. What is the sigma bond overlap, pi bond